Hello, math students. Mr. B here once again. All right, we are going to do some simplification of nth roots. And to start with, I want to do this problem. The third root, the cube root of 24. And to do this, I'll show you a sort of slow and hard way, and then we'll have an easier way to look at this. So if you think about it, 24 is 8 times 3, right? And 8 is 2 cubed. So you could write this as 2 cubed times 3, like that. And then we know that the nth root of A times B is the nth root of A times the nth root of B. So I can break this down into the cube root of 2 cubed times the cube root of 3. And so what do we get? The cube root of 2 cubed is just 2 times cube root of 3. And that's the answer. Here's a much nicer way to deal with this. Sort of like, often you can't really see these powers just by looking at the number under the radical. So a nicer way is to get the prime factorization of any number that's in the radicand, the number under the radical symbol. So let's do a factor tree. 2 divides into 24, 12. 2 goes into 12, 6. 2 goes into 6, 3. And 3 goes into 3, 1. Once we know that when we get to 1 on the right, the numbers on the left are the prime factorization of 24. All right, so the cube root of 24 could be written as the cube root of 2 times 2 times 2 times 3, and the index 3 tells us to look for groups of 3. Are there any groups of 3? Yeah, we've got 3 2s there. Well, anything that I've circled will come on the outside of the radical. We'll just get one number for every group. So we get 2 cube root of 3. The same thing we got before. Okay, now we can move on and do some more advanced problems. So let's say this is example 1 here, or example 2. Example 2. This is going to be the square root of 18x squared. So 18, let's get its prime factorization. 18 is even. Whenever a number is even, we know 2 goes in. So 2 goes into 18, 9, then 3 goes into 9, 3, and then 3 goes into 3 once. So we could write this radical as the square root of 2 times 3 times 3 times x times x. I'll expand the x as well. And because the index is 2, we want groups of 2. We want groups of 2. So do we have any groups of 2 here? Yeah, we've got a pair of 3s. We've got a pair of x's. All right, so we'll pull one item out from each circled pair. 3 times x, and a square root of 2 remains. Now there's one thing I haven't done. I've made a little mistake at this stage of the game. If you remember, if you have an even index, so nth root of a to the n, and n is even, then you have to have an absolute value on the result. So I need absolute value around this 3 and this x. Now the thing is, 3 is always positive, so the absolute value of a positive is just itself. So I could really write this as 3 absolute value of x square root of 2. I won't even write the index anymore because it's a square root. We need that absolute value. If we were told that the variables were positive, we wouldn't need any absolute value, but we weren't told that here. So, all right, another example. Example 3. Let's say we have the square root again, of 72 x to the 4th. So let's get the prime factorization of 72. 2 goes in 36, still even. 2 goes in 18, still even. 2 goes in 9. Finally, an odd number. 3 goes into 9, 3, and then 3 goes into 3 once. All right, so we could write this one as the square root of 2 times 2 times 2 times 3 times 3. And I know I expanded the x squared into separate x's, but I know that we're looking for pairs, right? We're looking for groups of 2. So let's break that x to the 4th into groups of 2. How about x squared and another x squared? That's 4x's, right? X to the 4th. Now we're looking for groups of 2. I'm going to circle groups of 2. We've got a couple 2's, there's a couple 3's, and then each of these squares is a group of 2. So on the outside, we're going to get a 2 and a 3 and an x and another x, leaving the square root of 2. Now, technically, we need this absolute value. We haven't been told that the x is positive and it's an even root again, right? Even root, we need these absolute values. So let's analyze what's in the absolute value here. I see that we're going to get 6x squared. And then there's the square root of 2. Now 6 is always positive, so we can pull that out of the absolute value. That would leave absolute value of x squared, square root of 2. And now think about this. If x is a real number and you square it, whether x is positive or negative, when you square it, you're going to get a positive number, aren't you? So we really don't need the absolute value here. We'll write the final answer as 6x squared, square root of 2. All right, one last example. Example 4. Let's get the cube root of 48 y to the 4th. So we need the prime factor expansion of 48. 2 goes into 48, 24. 2 goes into that 12. 2 goes into that 6. 2 goes into that 3. And then lastly, 3 goes in once. All right, so we can write this cube root as cube root of 4 2's. 1, 2, 3, 4 2's, a 3. And then we want groups of 3, right? The index is 3, so want groups of 3. Want groups of 3. And y to the 4th, we can get 1y cubed, and that leaves an extra y. I'm just grouping them sort of ahead of time here. All right, so what do we have for groups of 3? We've got at least 3 2's and 3 y's. So on the outside, we're going to get a 2 and a y, and then we have cube root of 2 times 3 is 6 and a y. Now, are we done? Do we need absolute value? No, we don't, because the index is odd. Remember, the nth root of a to the n is just a if the n is odd. So that's our final answer there. 2y cube root of 6y. All right, we'll see you in the next video.